Hello, my name is Jason Hernandez, and this is Jason Academy. It's a little like Khan Academy, but I only have one video, and most likely I can't help you with your other courses. Today, I'm going to teach you how to do a reaction involving 2R, 2-bromo, 3-dimethylpentane with methanol in an SN1 reaction. Now, SN refers to nucleophilic substitutions, in which we take a nucleophile, which is an electron-rich species who can donate electrons, a Lewis base. The nucleophile is attracted to an electron-poor atom who have electronegative leaving groups. Now, speaking of leaving groups, the first thing to happen in our reaction is that the leaving group breaks away. In our situation, our leaving group will be bromine. This is because of two reasons. Firstly, because it's the most electronegative atom in the structure. And secondly, because it has a relatively weak bond to carbon and will yield the most stable product. When our bond with bromine and carbon breaks, the electrons from the bond will go to bromine. Like this. The bond we had here is breaking, resulting in all the electrons from carbon and bromine to go to carbon. Now, this results in a positive formal charge structure. So let me draw that here. It also results in a bromide anion. So, much like Elvis, bromine has left the building. Now, usually at this stage, we would have our nucleophile, which in this case is the oxygen atom for the methanol, attack the carbon cation. But we have a slight problem. See, SN1 reactions prefer tertiary carbocations because of how stable they are. However, when our leaving group broke off, we formed a secondary carbon cation. Now, luckily for us, there's a way for us to fix this problem in which a tertiary carbocation can be formed. To do this, we perform a carbon cation rearrangement in the form of a 1,2 shift. Now, in a 1,2 shift, we can move either a methyl group with its electrons or a hydride, which is hydrogen and its electrons. So, to do a 1,2 shift, we'll make a carbon cation 1, and the closest carbons to it, 2. Thus, the reason we call it a 1,2 shift. Now, it's important that our shift results in a tertiary carbocation and not another secondary carbocation. That's in order to make sure that this stays as stable as possible and make sure it's good for the SN1 reaction. So, we can't necessarily take it from here, because if we were to take a methyl group or hydrogen from here, we would not result in a tertiary carbocation. However, if we take it from here, from one of these two methyls, we could potentially end up with a tertiary carbocation. So let's use this one, for example. And we end up, well, firstly, in this situation, we end up moving this methyl group to the carbocation in this 1,2 shift. So we finally end up with this structure, and now the carbocation is in a tertiary position. So this allows us to move on to our next step, in which the nucleophile attacks. Now, for us, our nucleophile will be the oxygen atom of our methanol. So let's draw out the methanol real quick. There we go. The electrons from our oxygen are going to form a bond or attack our carbocations. So, demonstrate this really quickly. Now, this can attach from either top or bottom, and I'll explain what I mean by that in a few minutes and why that's important. We now have a new bond in which oxygen still has its lone pair. So let me finish drawing out this entire reaction. So here is our new structure now that we've bonded. Okay. Now we have a new bond from oxygen, who still has a lone pair of electrons that have yet to react, and it has a formal charge, as well as the carbon and the hydrogen still present. Now, for our reaction, our main product of interest will not have a formal charge. This means you're going to have to go through one more step called deprotonization. Deprotonization implies an acid-base reaction, in which our intermediate of interest is the acid. This is our acid. And our methanol, our nucleophile, is the base, as I mentioned before. Methanol being our base is going to take a proton from the intermediate. Well, firstly, let me clarify that here is, here it has a proton. So the oxygen is going to take a proton from the methanol, causing the oxygen-hydrogen bond to break, putting all the bonds into the oxygen, and it provides us this structure, which will be our final product. as well as H2O with a positive formal charge, CH3. And that's what we get from our prior methyl. Before we finish, I want to also clarify, or I want to specify why this is necessarily an SN1 reaction. And we can show this through a couple different methods. Firstly, we can show that the rate is not dependent on the nucleophile. This means that our rate determining step is unimolecular. Now for us, our rate determining step, the RDS, is our first step in which the leaving group breaks away. And for us, that is going to require the greatest amount of energy. Secondly, we can show that this is not a stereoselective reaction. In the beginning, we may have noticed that Br has an R stereochemistry. However, we learned down here that the nucleophile can attack from either the top or the bottom. That means that we can have a mixture of R or and S stereochemistry. So, as a result, potentially, you could have both your products look like this, in which you have a wedge, or potentially, you can have a product existing as a dash with no exact preference. Neither one has exact preference because it is not stereoselective. Before I mentioned that we needed to make sure that they were tertiary carbons, and you may be wondering why tertiary over secondary. Well, we use tertiary because it's the most stable for SN1 due to induction. For all alkyne groups, electrons from neighboring carbons are donated via induction. So, for example, if I have a carbon here, I'm more likely to receive more electrons via induction from these groups here. I have three different carbons providing me electrons, versus if I only had two. Now I'm only getting electrons from two carbons, which would be a secondary. This is a tertiary. Or if I had just a primary. Well, that's all we have for today. Thank you very much for checking in on Jason Academy.